On the last lecture, we stated the following error formula for Newton-Cotes rules. So, error bound for Newton-Cotes rules of order M is the following. Integral from a to b f of x dx minus quadrature, which we have found using Newton-Cotes rule. So bounded on the top, this absolute value is no more than some constant Cm, m d plus 1 minus a m minus 1 to the power d plus 2. Here d is m minus 1 equals to m minus 1 if m is even, and equals to m if m is odd. Okay, and this constant is just a constant which is just defined only by m. Pay attention, so it doesn't depend on the function. Yeah, m d plus 1 is a uniform bound on the essentially maximum. Oh, it's better to write it like that. F d plus 1 of x magnitude. So magnitude of the d plus 1's derivative of the function of our function under integral sign is bounded on the top by m d plus 1 on the whole interval for x belonging to the AB. So pay attention. This beliefs depends on the function. So different functions have different properties. So this bound will change based on the function. See, this constant depends only on the order of the rule which we are using. So, and they are given, so you can find them in Abramovitz-Tigun or other books. So they're relatively small constants. So by small, I mean way less than 1. So for example, for C2, it's negative 1/12. And the further you go, the smaller they become essentially. Okay, so as I said, so what is the approach? So if you need to integrate your function over the large interval, then you could say that, okay, but then I need either to use crazy high order of the Newton-Cotes rule for a small error, right? Small error bound, because using the order, I can decrease this constant, right? But this constant is decreasing pretty slowly. And at the same time, if you have pretty large interval, this will be, this term will be increasing, giving you more and more troubles. So if b minus a is large, so when you increase m, you increase this power, right? And you're getting in trouble. Okay, so then what is the approach? So the easiest way would be to consider small interval b minus a, right? From the other point of view, you could tell me that A and B are given in our integration problem, right? So what can we do? As I explained on the last lecture, so if you have large interval from A to B, you can split it into equal subintervals. So yeah, they do not look that equal on this picture, but let us suppose that they are all equal. And this H is nothing else but B minus A divided by the number of subintervals. And then increasing this number of subintervals, you are decreasing this H. So on every of these subintervals, so error bound is the following, that it's the same CM, right? Then you can use the same MD plus 1, because if this is the maximum essentially, or the maximum bound for the whole interval, so on subinterval it also will work, right? But here you will have H divided by M minus 1 to the power D plus 2, right? So, and when you will be decreasing H, increasing the number of subintervals, what you will get? You will get essentially that the error will be decreasing. And the faster, it will be decreasing faster, the higher, usually, pay attention, the higher is the order, because D is related with the order of the Newton-Cotes rule. Okay, so for example, you could say, but Newton-Cotes rule required several points, right? Okay, so then you consider these. For example, if you want to use Simpson, you consider these 3 points, and then these 3 points, and then these 3 points, then these 3 points, then these 3 points. And with this point, so we can consider different situations, but usually you choose N in such a way that it would give you the right number of subintervals depending on the order of the, so you would get a multiple of the order of the your Newton-Cotes rule, so essentially how many points you need to use. But what you can do, usually you can either stop here, and for small h, you can consider expansion of your function and approximate analytic evaluation of the last part, or in the worst case scenario, just to be simple, so you can make one trapezoid step, which will decrease the accuracy a little bit, but still there are different approaches. But usually, because you control this number of subintervals, so you choose this number of subintervals in such a way that it's multiple of the number of points you need, so that you don't have this trouble. So pay attention now that we don't need to evaluate our function twice in this point, for example, right? In this point. In this point, we also can use evaluation of our function here. In this as well. And so on. So we can save it. So let us represent this. So essentially, our integral from a to b, f of x dx. Okay, let me call this x naught, x1, x2, x3, x4, x5, x6, and so on till this is xn, and this is x, and so on. So I will just represent it as sum over subintervals. And here I will use just, for example, let's say 1,6 f of x naught. Let me just write it without the sum sign for now. 1,6 f of x naught plus 4,6 f at x1 plus 1,6 f at x2. And all these multiplied by h, right? So this is our Simpson formula. Plus, now, next subinterval, this one. So I'm using 1,6 f at x2 plus 4,6 f at x3 plus 1,6 f at x4, also multiplied by h. Okay, in this case, no, it will be 2h, because you see, we said that h is here, right? So here it will be 2h. So in other words, here it will be mh, yeah, like that. Okay, m minus 1. Okay, plus one. So let us go further. Let me check whether it's supposed to be 2h or no, I believe here it's supposed to be like that. Yeah, because yeah, this is the right form. Okay, next. You can continue like that. So 1,6 f of x4 plus 4,6 f of x3 x5, sorry, x6 h plus and so on, plus, and here will be the last part. So let us say that we have chosen the number of points, right? Really, I can correct this here, like that. I will just say that here is my b, and this is my xn. This is my xn minus 1. This is my xn minus 2. So what is interesting, so of course you don't need to do function evaluation twice at x4. So what you can do, you can just bring them together, and then you will get 1,6 f of x naught plus 4,6 f of x1 plus, look here, this and that together will give you 2,6 f of x2, right? Then this term we encounter just once, right? So the middle point. Then here and here, again, term comes into sum twice. Sorry. Okay. Then this term comes once. And this term, because next term here will contain it again, so will be 2, 6. And then it will be 2, 6. This term will have its counterpart here. This we encounter just once. And all that multiplied by h. So you see, this is what we are getting. And points they come with the 1, 6 weight, but all points inside of the interval, they are coming with alternating weight 4, 6, 2, 6, 4, 6, 2, 6, and so on. So as a result, you can see that in this, if you are starting from x naught, so then odd indices will give you 4, 6. Even indices will give you 2, 6, right? So as a result, you can just write it like that. Okay, I will, I can factor out 1, 6, right? H over 6 multiplied on f of x naught plus this will give me 4 on the sum odd I f of xi plus 2 sum even I f of xi plus the last term f of xn. And this is how you should compute it. Please don't write the loop with if checking whether I is even or odd, and then multiplying by corresponding like here by corresponding weight, because the comparison inside the loop is very inefficient. It breaks it decreases computational efficiency significantly. So if you like to know about it, so please read what is pipeline in the processor and why conditional switches in the program are not so good for efficient utilization of pipeline. So this is why it's better to go over, compute the sum over all odd indices, multiply by 4 the whole sum, because in this case you're also saving multiplication, right? So instead of multiplying every term, you multiply just once already the computed sum. Here you do the same for even indices, then multiply by 2, then you add to these two values, so on the endpoints, and multiply by the h divided by 6, where h is the step of your, so essentially h is b minus a. Let me remind you this. Okay. So now, this is what is called composite rule. Why it's composite? Because you, first of all, considered subintervals, and then have a look. You took into account, so like here, this term and this term, you took into account that this term is coming twice in the total sum, and just as a result, you replaced it with the one coefficient, these 2, 2, 6, 2, 6, 2, 6. So you took these elementary rules for every subinterval, but for efficiency, you took into account that some terms are coming twice into the into the sum, and use this information to make it computation more efficient. Okay, so of course you can do something similar for the open intervals, open subintervals. So you will get something like that. So you can split this like that, and then you will be evaluating your functions only in the internal points here. But I can tell you the following. So in my practice, I never encountered that. So practically never people do this. So what people usually do is people are using this formula. Simpson, because it's very easy, or trapezoid. So for trapezoids, it's also interesting. Let us do this. So this is x naught, a, b, x naught, x1, x2, x3, xn, xn minus 1. Okay, so what to do in this case? You use for trapezoid these 2 points. Then for the next subinterval, you use these 2 points, 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 and like that further. So everywhere here you have subinterval h. Then this is what you are getting. Maybe could you maybe help me? So so we can approximate our function. Yeah, as usual, h is b minus a divided by n. So trapezoid on the first subinterval, what it will be? H divided by 2, right? Okay, unfortunately I don't have time. So this, is it clear or not?
Yeah.
Okay, so on the second subinterval, it's this. Third subinterval is this. So this plus that. Plus and so on. And the last subinterval will be okay. Once again, we can use composite rule here in the following way. So we can factor out h divided by 2. And then inside we will have what? We will have f of x naught plus this comes twice, right? plus this comes twice. This, as you understand, also will come twice. And so on. This will have its counterpart here. Just like that. So then, usually people write it in this form. Just easier to compute it like that. 1/2 f of x naught plus f of xn plus sum over internal points. Just like that. So this is composite rule for trapezoid. You can, so I can tell you that essentially in my practice, practically the only rules, I mean, not only, I had to use something more advanced sometimes, but in majority of applications, you will use either this trapezoid if you cannot use information about 3 points, or if you are more free, so you will use Simpson, composite Simpson rule. So everything more advanced, it's pretty rare. So people use it, but relatively rare. Okay. So error formula. So idea is the following. So this is the error formula for one here, this one. So error formula for one step. Okay, the problem is that you will have not one such subinterval, but many subintervals. And on every subinterval, your error is bounded by that. In worst case scenario, all of your errors will add up. So essentially your error, so yeah, let me give you the explanation. So error on a subinterval is called local error. Error on a whole interval, including all subintervals, all n subintervals. This is global error. Okay, so idea is that the local error for the local error is for example, it's like that. So you are replacing, okay, let me write it. Let me call this using n subintervals. So less or equal than, so Cm stays because it cannot be changed. I will use the same maximum bound for the d+1's derivative of my function, absolute value. And then here I will have h. divided by m plus 1 to the power d plus 2. So everything is the same, but h is nothing else but b minus a divided by n, right? So you can say that this is cm, md plus 1. Here is b minus a divided by m plus 1, exactly as before. Sorry, minus 1 here. Minus 1. D plus 2. And I will factor out these to this power. So it will be 1 over n to the power d plus 2. So the more subintervals I'm considering, the smaller is this h, right? And the smaller is the local error or error on every subinterval. And the higher is the order of the method, the faster this factor is going down with the increase of the with increase of the number of subintervals. But the problem is that, as I said, in the worst case scenario, you all your errors. So this is the local error. Yeah, in the worst case scenario, what you're getting, you're getting that your errors will add up. Okay, for example, let us consider it like that. For the Simpson rule, we know that m is equal to 3, right? So d is equal to 3, and then we are getting that your local error for Simpson is proportional to h to the 5th, right? Have a look. 3. Simpson is m equal to 3. Odd, right? So then d is equal to 3. Substitute 3 here, right? So you're getting 5th power for the length of the interval which you are using. Okay. So you are getting h to the 5th, right? But now, number global error worst case scenario. So is number of subintervals multiplied on h. So we'll scale as number of subintervals multiplied on h to the 5th, which will give you n multiplied by b minus a divided by n to the 5th power, right? So result is that you are getting b minus a to the 5th divided by n to the 4th. Or you can say that this is b minus a multiplied on h to the 4th, right? Okay, so have a look now. If you so could you tell me how the local error for the Simpson rule will change if I increase number of points, if I decrease h twice, or it's the same as if I so let me again remind you this. So really I don't like it, so it looks kind of strange. Yeah, Okay. Let us believe our notation and our records. So could you tell me how the error will change if I increase number of points twice? If I increase number of points twice, how the x will change? H will change. Hello, anybody? Can you hear me?
Yeah, we can hear you.
So b minus a stays the same, right? I increase these twice, and how h will change?
If you double the number of points, then h will decrease by a factor of 2.
No, h will decrease twice, right? So if I double the number of points, h becomes twice smaller, right, than before. Clear or not?
Yeah, that's good.
Okay, it means that the local error, which is proportional to the h to the fifth, right? Because have a look, this stays the same, right? Because this is a constant, this is the bound on the function, right? So b minus a stays the same, right? So what will happen with the local error? How it will scale?
It'll decrease by a factor of 2 to the 4.
No. Local error, because it's a proportional to h to the fifth, right, will decrease by the factor of 2 to the fifth, right?
Yeah, sorry.
How much it is? Do you remember? It's 32 times. 32 times. So you increase the number of points just twice, but your error decreased 32 times. At the same time, because there will be more subintervals, twice more subintervals, right? So your global error will decrease just 16 times, right? Clear or not?
Yeah, that's clear.
Okay, now let us consider the case trapezoid. Trapezoid rule. Local error. Okay, based on this formula, d. Okay, m is equal to 2, so it's even. So d is equal to 1. So it means that here I will get h to the third power, right? So local error is proportional to h to the third power, right? Okay, then global error. So we always, because we are multiplying by n, right, like here, we always lose 1 power. So it's h to the second. Now, I'm asking the question. So if I increase n, let's say 5 times. So how h will change? I mean,
It'll just decrease by a factor of 5.
Right. Okay, could you tell me how this error, what will be the, how the local error will change?
It'll decrease by a factor of 5 to the third, or 125.
Mm-hmm. Okay, how the global error will change on the whole interval?
It'll decrease by a factor of 1 over 5 squared, or 1 over 25.
Okay, any questions here? So do you understand what is going on?
And yeah, I think on the composite Simpsons rule from earlier, isn't it supposed to be h over 3 instead of h over 6 is the...
This is what I'm a little bit worried. So you probably heard it. So because in our notes it's 1 to the 6, unfortunately. But let me check. Okay. Let me check it once more. Because I also remember it like you said, so, but it's probably different definition of h, because maybe here in our notes h is the length of the subinterval. Okay, let me have a look once again. Yeah, h is a subinterval. Okay, then everything is clear. Yeah. Yeah, this is exactly what I thought. So when I was trying to put their different lengths, so okay, h is the length of the subinterval. So then here for trapezoid everything is right, but for Simpson the length is, it's really wait a little bit, yeah, 2n, because we use, yeah, in our notes they use this as h, but in order this, I mean, you will never use it in your life. So normally you would just consider it like that, to h, to h, to h, to h. Yeah. And then it's h divided by 3 here. That's it. Okay, for trapezoid, everything is right. So yeah, thank you very much for this comment, because just I was also surprised, but yeah, it's because in our notes they consider h is as the length of the subinterval here. Then here it will be 2 or m minus 1, right here, but it doesn't matter. So it doesn't change really the scaling, which is important. Okay, so then here we are getting h over 3, here to h, yeah, everything is right now. So let me correct it. Yep. Okay. So now so in most of the cases people use homogeneous grid or grid with even just split the interval of integration into subintervals of the same length. So using just this formula. Now, the question is the following. Can we do better? If you have done problem 3 in your homework, you know that we can. So have a look. If you are using Newton-Cotes rules with even subinterval, so then what you are getting that here for order m, you have correspondingly bound on the derivative of the order d plus 1, right? So as you remember, when we were doing polynomial interpolation, we had something similar. We had the error bound, right? But then we said that, but still we had Runge phenomenon, right? And then we said, why we have to limit ourselves by the homogeneously spaced points, so, or evenly spaced points. And then we introduced Chebyshev polynomials. So then we have shown that if you choose the grid where the points are located, the grid points are located at the zeros of the corresponding order Chebyshev polynomial, then these would give you minimal error bound, so which is maximum of the minimum, right? Minimum of the maximum, sorry. Minimax problem over the interval for the polynomial interpolation. Minimum of the maximum error. Okay, so in the case of integration, you also can do something similar. To put your points not in the not over the not evenly. So, and then it appears, so essentially in your homework you already saw it. So what for Newton-Cotes, so what we used some h multiplied on sum, and here we had f of wi, f of xi, I goes from 1 to n, and xi were evenly spaced points. Spaced points. So now the question is, if I will do not consider evenly spaced points, can I do better? So as you saw in your homework already, so if you are saying that you consider evenly spaced points, the only freedom which you have is the choice of these weights, right? And then you're getting linear system of equations, and you are requiring that your integration would integrate these polynomials of degree up to something, right? And this is what and you are getting a system of linear equations which allows you to determine these weights. Of course, you can compute them in different ways, just directly integrating the polynomial and so on. So then there is Gaussian quadrature. which says that, okay, let us consider not only weights as free parameters, but also let us consider positions. So essentially, so A plus C I. So positions of these points as free parameters. So here we had essentially A plus I minus 1 multiplied on H for, no, just I, like that. And these were equally spaced points. But here we can say that, okay, let us consider some non-homogeneous spacing of points. And this doubles essentially the number of parameters which we can choose. And as you saw in problem number 3, it allows you, so now of course you will be solving the quadratic, I mean, not quadratic, nonlinear system of equations, but you can still find them. Okay, now if you like, you can read our 5.5 section, but I will just state the results from there. So essentially, they are the following. So you don't necessarily need to solve the system of nonlinear equations. You can show that these are these positions are nothing else but zeros of the Legendre polynomial. Which are defined like that. So pi of x 1 over 2i I factorial di by dxi of x squared minus 1 to the power I. Or you can write it also a little bit differently. So this is what people usually do. So it's nothing else but ith derivative. So this is an example of orthogonal polynomials. So you can introduce analog of the dot product, but on the space of polynomials. And if this analog, it's called inner product. If inner product of two polynomials is equal to 0, we call these polynomials orthogonal. So then you can formulate the following, that essentially if you use zeros of these polynomials, which are tabulated, so then you can prove that the following theorem Gaussian quadrature method using degree n Legendre polynomial. The interval from -1 to 1 has degree of precision n minus 1. Okay, so you could say that, but what is the difference, right? The thing is that polynomial of degree n has n zeros, right? So if you are using exactly, I mean, up to multiplicities. So if you are using n points in your interval, you're getting, unless you're, so have a look. If you are using n points, it's essentially the order for the Newton-Cotes rule. So your error scales linearly with the number of points, because d is more or less, it increases more or less like m, with just a little bit better result for the odd number of points, right? For the odd order. So you see, your d is, you can say that for, especially for large m, it's almost m, right? So for example, if you consider 6 points rule, right? So your d is either 5 or 6. I mean, for 6 points rule, yes, your d is 5. But for a 5 points rule, for example, your d is 5 again. So 5 points rule. And what is change? What it is changing? It is changing. Where it is here? Exactly this power, right? So essentially, if you increase the number of points by some factor, so how your error decrease, global and local error, how they will decrease. Okay. In this case, for example, 5 points rule, Gaussian with Legendre points, local error is proportional to the length of subinterval to the power 2 by 5 minus 1, which is h to the 9th. And global will be for the composite rule. So you would have something like h to the 8th. So the difference is the following. If, for example, you use so Newton-Cotes 5 points, so local error proportional to the h to the 5th, and global error proportional to h to the 4th. Is it right or not? Mm-hmm. No, of course not. So m equal to the 5d. Okay, this is 7. And here we have 6. Right. So you see, difference is the following. For example, you have h, which is about 0.1. So here you will have for global error 10 to the minus 6. Here you have 10 to the minus 8, 100 times better. So feel the difference. But also, what does it mean, this degree of precision? So it's essentially, it also gives you a limitation on the derivative of this degree. So Gaussian quadratures, although I don't think that you will ever program it by yourself, although it's possible. So, so Gaussian quadratures can allow you, just using the cleverly spaced points, can allow you to get higher accuracy using the same number of function evaluations. Because what is the complexity of the how you decide what is the complexity of evaluation of the numerical evaluation of the integral? You essentially have a look how many function evaluations you need to do, because of course multiplication by the weights and so on, it's important, but not that important. So usually the hardest part is to evaluate, for example, for this composite rule, to evaluate the function at every point. So usually this takes the most of computational resources when you do this evaluation. So as a result, what Gaussian quadrature method does, it allows you to do to get higher order accuracy without changing the number of evaluations of your functions. Okay, I will stop here. Talking about quadratures, numerical quadratures. So, and now let me start talking about initial value problems for differential equations. Initial value problems for ordinary differential equations. So, what is ODE? So let me consider the following simple formulation. Really, there can be different formulations, but this is one of the most, not the most, but one of the most general formulation of ODE. So essentially, you are trying to find the function y of x, so this is derivative, right? Such that it satisfies this equation, where f is almost function. There are some limits on smoothness. And how you and usually you have initial condition, so that at x equal to 0, or if you like at t equal to 0, instead of x we can use t. We know that our function is equal to some value. So this is given, and this is given. The function is given. And you need to find y of x satisfying this condition. So this is initial value problem. Why initial value? Because the value of your function is specified at initial moment of time or at the initial point on x. And you need to find these usually up to for x belonging to the interval from 0 to some value t, capital. So essentially, you are trying to solve this equation. The problems of this type appear in mechanics. I mean, I believe that you already encountered ODEs. So they are even, I believe, covered a little bit in the calculus classes. So, okay, now what to do with that? The simplest approach. So let us remember what is this? What is the derivative? Like that, right? It's one way of defining the derivative, right? So what we can say, we can just say that let us approximate, and we did it before, these with, okay, let me call this H. For sufficiently small then our equation will look like that. Right? And from here, you can write that x plus h equals to, oops, sorry, why? Can you hear me? Why nobody corrects me when I'm writing the completely wrong things? Right? Is it clear or not? What I've just done?
Yeah, this is clear.
Okay, so it means that I can do the following. Let us split the interval y into small subintervals x I plus 1 minus xi equals to h. And then I can write that y xi plus h, which is nothing else according to this, nothing else but h xi plus 1, right, equals to y xi plus h multiplied on f and I can just continue over. So if I start, so for example, x naught is equal to 0, and I know that y at x naught is equal to y naught, right? So then I can get my y at x1 using this formula. And okay, of course, yeah, here approximate equality. So I can get my y at x plus 1 using this formula, and I can continue until I will reach my desired x equal to t capital. And this is called Euler's method of integration of ODE. You can derive this method in the following way. Just remember, this is what we had. Let us integrate left and right hand side from xi to xi plus 1. And as I said, distance between them is equal to h by dx. And here the same. So here, because it's full derivative, we know that it will be y xi plus 1 minus y at xi, right? And now what to do with this integral? We already studied numerical integration. So we know that in some cases you cannot just find entire derivative, but what you can do? You can try to apply one of the numerical integration methods, right? Numerical quadratures. So let us approximate it by using, for example, left rectangle rule. Could you remind me what you use? So could you tell me what we will get?
It would be xi times h.
Not xi, but f at xi, right?
Oh, yes.
So, right, thank you. Times h, right? So left rectangle rule. And then from here, we immediately get in Euler's method, right? Okay, but we know way better approaches, right? We can do, for example, trapezoid method. Then what you will do? You will get exactly the same thing in the left hand side, right? Because it's just integral of these. But in the right hand side, you will have h divided by 2 f y xi plus f y xi plus 1 xi plus 1. Right? The only problem is that you don't know this, right? You don't know this y at xi plus 1. But what you can do, let us consider this to be y tilde approximation. And for this approximation, let us use Euler's method. So this is how you get next order method. So y xi plus 1 approximated by yxi plus h divided by 2 where this is computed using this formula. And this is because we know that numerical integration has higher order and lower, I mean, in most of the cases, lower error, right? So this is how we get it. So, okay, this is Euler. Euler's method. And this is often called improved. But pay attention that for improved Euler, you need to compute first approximation of our function at the point xi plus 1, then substitute it here, and then you will get this result. So you see, you are getting higher accuracy not for free, but for more work.